Hi, good morning. Welcome to the lecture. In this lecture, we'll talk about radical reactions. When we discussed the types of chemical mechanisms, we talked about two main types of termination mechanisms. Those mechanisms are homolytic cleavage and heterolytic cleavage. Homolytic cleavage is where if you have a bond XY, you have two electrons here. Each electron goes to one each of the atom. So we end up with X plus Y. So in heterolytic cleavage, we discussed that if you have a compound XY, so it splits into only one side. So that results in X positive plus Y, two electrons negative. Now, so remember that homolytic cleavage creates radicals and heterolytic cleavage creates ions. So what we discuss now in most mechanisms is ion mechanisms where you have two charges. For example, nucleophilic and addition reactions mostly involve a nucleophile and an electrophile. Most probably a nucleophile is a negatively charged compound and an electrophile is a positively charged compound. Now in this chapter we are going to focus on homolytic cleavage. The other name for homolytic cleavage is homolysis. So homolysis, so lysis means to split, homo means to split equally. So here the two electrons are split equally among the atoms. So one specific characteristic of a radical is it has no charge. So it has no charge. Now, so to represent when we write an arrow, this represents the motion of two electrons. And when you use a fish hook, so the fish hook represents the motion of one electron. So you will see much less of this in this chapter, and we'll see more of fish hook mechanisms in this chapter. So if you remember, we used to use this in resonance structures. So this is most commonly end up used in radical structures. So single hooks are generally used for radical structures. So radicals have two types. One, you can have a carbocation. If you remember, there are two types of structures that can be formed. One is a carbocation, the other is a carboanion. Carbocation has an empty p orbital. So that empty p orbital results in an sp2 hybridization, which is a trigonal planar structure. But when you have a carbon anion, so because of the presence of the two electrons on one side, it results in an sp3 hybridization with a lone pair of electrons. So it results in a trigonal pyramidal structure. But when you take the same thing for radicals, radicals are generally trigonal planar or shallow trigonal planar, meaning that they can be sp2 and sp3 hybridized depending on what structure we look at. If you have a trigonal planar structure, remember that in place of two electrons, we still have only one electron. That's the reason why it's still trigonal planar and still sp2, not sp3. For a shallow pyramid, it generally results in a rapid inversion of a structure. So where it can be either on the top or on the bottom. So here it's equally distributed. It's distributed only on the top, but here it's trying to be distributed on both sides. Next, in terms of the stability of the radicals in general are neutral, which means they do not have any formal charge. But because of the electron deficiency, they are still electron deficient, meaning that they have an incomplete octet. So radicals follow the same stability as that of carbocations. So the more the substitutions that they have around the carbon atom, the more stable the atom. For example, if you have a methyl radical and if you have a primary radical and if you have a secondary radical and if you have a tertiary radical. So the difference here is the stabilization of the electron. Electrons are always stable when they are free, just like a carbocation. So the more focused they are on one point, so the more substituted the size. So as you go from methyl to a tertiary compound, it results in an increased stability. So tertiary are more stable in comparison to methyl, which are less stable. Now, bond strength here is inversely proportional to the carbon radical stability. So the less stable the compound, the more the bond dissociation energy. And the more stable the compound, the less the bond dissociation energy. Now, free radicals in general, they act as carbocations, so they are also stabilized by resonance delocalization. So what does that mean? If you take an allylic carbon, so remember that in this structure, we have 3 carbons here. So these 2 are vinylic carbons. This is an allylic carbon. Now remember that allylic carbon is here the more stable, electronic structure. So what happens here is that rather than the electrons staying in their own place, if you have an allylic radical, say if you have an allylic radical, this results in a motion, so where this electron goes here, and the 2 electrons that are present here, one electron will come here and the other electron will go here, so resulting in a structure that would look somewhat like this, where the radical comes here and the double bond goes to the other side. So these two combine to form a bond. So this process is called the resonance delocalization. So the process of delocalization is its ability to move. So the ability to move comes from resonance structure, so that's why we call it the phenomenon as resonance delocalization. Now, the more the resonance delocalized the radical is, the more stable it is. So, for example, benzyl radicals are generally more stable than allylic radicals because the radical is much delocalized because of the number of carbon atoms that can move. So, the more it can move, so the more the radical can move, more stable it is. So the more it is fixed, the less stable the radical. So here the electron can move to about 1, 2, 3, and 4 different positions. So this results in a more stable structure. So in comparison to a tertiary structure, which we said that is more stable in the general structures, an allylic carbocation, an allylic radical is much more stable than a tertiary radical, and a benzylic radical is much more stable than an allylic radical. So when you take a compound, and if you consider that which carbon is going to be the most stable compound, the benzylic radical is going to be the most stable one, and always ready to react in radical reactions. So remember that these are always ready to react in radical reactions. That's the reason why they have less bond dissociation energy in comparison to a tertiary radical. So they are generally more stable. So the stability goes from methyl radicals and entirely towards benzylic radicals. In terms of the double bonded structures, vinylic radical is much less stable than an allylic radical. It's so less stable that it's generally less stable than a primary radical. So vinylic radicals are generally unstable, and they will never involve in radical reactions as much as possible. So a radical in an sp2 orbital is generally less stable than one in a sp3 orbital. So this is the common sense in which we handle around the structure. So what are the common patterns that we see? So just like the patterns in resonance mechanisms where we discuss the structures of AR-IO mechanisms, so we also have different radical mechanisms that undergo the same reaction. So one main differentiation between like ionic mechanisms, radical mechanisms also follow patterns, but radical mechanisms are generally distinctively different. So the main example of that is radicals do not undergo rearrangement. So this is important because if you remember, carbocations always rearrange to more substituted carbon, but radicals do not undergo rearrangement. So wherever the radical is formed, it stays there unless it is resonance stabilized. So only under resonance delocalization where it moves by itself, it does not rearrange towards a more substituted carbon. Now there are 6 key arrow pushing mechanisms that we generally see in radical mechanisms. So let's see one by one. So this is the first one, homolytic cleavage. So where we talked about where 2 electrons between the bond are equally shared by the radicals. So this happens either by light or by heat. So the most common way of seeing this is a delta or H nu. The addition of a pi bond is where if you have a radical and if it approaches a double bond, so the double bond with these 2 electrons, so the radical donates its electron and the double bond donates its electron. So they both result in a bond formation, and this electron goes here. So this results in X and a radical. So this is the structure that results in. So this mechanism is the addition to a pi bond. Next is the process of hydrogen abstraction. It's not the same as proton transfer. So what's the difference then? So here you have a radical and you have a structure of HR. Now in a proton transfer, we are looking at a proton. Proton is generally a H plus molecule, but here hydrogen abstraction results in just hydrogen with its electron. So what's the difference between a proton and a hydrogen radical is that hydrogen is not charged. It's not charged. Proton is charged. So that's the difference between a hydrogen radical and a proton. So now what happens in this mechanism? It's similar to what happens before. So you have 2 electrons. One of them goes towards hydrogen. The other goes towards the structure, and this radical supplies it to the hydrogen. So this results in XH and then R becoming the radical. So this is the process of hydrogen abstraction. So there is a process of hydrogen abstraction. Next is the process of halogen abstraction. So it's similar to that of hydrogen abstraction. So you have a radical R, so that has an XX bond. So here one of the radicals will go here and one of them will go here, one of the electrons. This R supplies the electron here, so this results in RX plus X. So this is the structure for halogen abstraction. Next is the process of elimination. So elimination, so we already know that this is the reverse of addition. So in elimination, the radical on the alpha carbon is pushed towards the beta carbon to eliminate the radical. So best example of this is take the example of halogen abstraction, the addition of a pi bond. So where we have X. So what happens here in this mechanism is that this supplies an electron here. This with two electrons supplies an electron here, and one of the electrons will go back to the radical itself. So this results in EX formation plus you get a double bond. So this is the process of elimination. So what happens here is the alpha carbon. So the alpha carbon is this carbon, donates its electrons to the radical. So it takes the electron from the radical. So it donates the electron from the radical and takes it away. So that results in the elimination of the structure. So here, this is the alpha carbon and this is the beta carbon. So alpha carbon is always the one with the radical. Remember the main structure is that beta is adjacent to alpha carbon. So this is the process of elimination. Next, the final process is coupling. So coupling is the reverse of homolytic cleavage. So if in homolytic cleavage we have two radicals that form, the two radicals then combine their each electrons and then form the bond themselves. This is the process of coupling. So most common coupling is generally seen in the termination of a radical reaction. Most elimination mechanisms are also seen at the termination of a radical mechanism. So we'll discuss this as we go along in the chapter. Now, so these are the common ones. In forward, it's homolytic cleavage. In reverse, it's coupling. In forward, we call it addition to a pi bond. In reverse, it becomes elimination. In forward, it's hydrogen abstraction. In reverse, also, it's hydrogen abstraction. Here, hydrogen abstraction first happens by the radical. Here, the radical that creates then again abstracts the hydrogen. So this is the patterns. These are the 6 patterns that you generally see. And there are only generally 3 processes. So one of them is forward, one becomes the backward of that process. Next, what are the common patterns in radical mechanisms? There are 3 main of them. One is initiation, termination, and propagation. So what happens in initiation? So initiation is where the radical species are formed from a non-radical species. So initiation generally happens by homolytic cleavage. So initiation generally happens by homolytic cleavage. Next, propagation. Propagation occurs when a radical reacts with a non-radical species to form a new radical. So propagation, they can happen in 2 mechanisms. One, it can happen to the addition of a pi bond, or it can happen by hydrogen abstraction, or it can also happen in elimination. So this process is also the formation. So this process, these are the three processes that undergo in the process of propagation. Next is termination. Termination is where the two radical species then form the non-radical species. So termination reaction most commonly occurs in the process of coupling. So coupling is the main process that determines the process of termination. So remember the three main processes. Initiation, propagation, and termination. So initiation is where the radical species are formed from non-radical species. Propagation is where the radical species attack non-radicals to form radicals. Termination is where the radical species form non-radical species. So if you remember these three mechanisms, then this entire chapter becomes the easiest it can. So let's look at the first mechanism, chlorination of methane. So chlorination is also a radical mechanism. So again, it consists of three distinct steps. So the common reaction is CH4 plus Cl2 forms CH3Cl plus HCl. So this is the mechanism that happens. This generally happens in the presence of chlorine and UV light. So let's look at the first step. So the first step is initiation. So remember that initiation is where the radical species are formed. So between the two reactants, chlorine has the more chance of having a radical species because it's a halogen. So chlorine Cl2 is Cl bond Cl. So under the presence of UV radiation, this creates the Cl radicals, Cl and Cl. So this is the process of initiation. So the first process is where the homolytic cleavage takes place. Now, remember that chlorine in general has 6 electrons in its outer shell. So you have the 6 electrons plus 1 electron. So they have 7 electrons each on their outer shell. Now let's take the example in the next step, so which is propagation. So what happens in propagation? So propagation is where radicals mix with non-radicals to form radicals. So what happens here? So in the first step, you have a methane molecule. A methane is carbon with 4 hydrogens. So one of the chlorine radicals comes close. So it undergoes hydrogen abstraction. So the hydrogen here takes its electron, and the carbon takes its electron, and the chlorine takes its electron. This results in a primary radical formation. So it creates the primary radical, plus it creates HCl. So this is the process of propagation. Next, in the process of propagation, then it creates many more structures like these. So it can happen in multiple procedures. For example, you can have the chlorine as well. Undergoing a radical mechanism. So this can also result in the radical formation. Plus HCl plus a Cl formation. Notice that this is a radical, this is a radical. So there are two radicals in this reaction. So it can either occur by this mechanism, which is hydrogen abstraction, or it can also happen by this mechanism, which is halogen abstraction. So now we have formed the radicals. In the next process, it undergoes coupling. So the last process is termination. So what happens in termination? So if you have a free primary radical, with another chlorine radical, so each donate their pair of electrons and result in methyl chloride formation. This is number one termination. Number two termination is to terminate the radicals as well. So the other radicals that are there is, if there is a hydrogen radical that is not involved in the reaction, that hydrogen comes back again and comes back and forms methane again. So this is one, this is number two. And three is the chlorine radicals that are present. If they do not mix with anything else, they end up mixing with each other and form ClCl back again. So this is the process of coupling. So, sorry, this is generally something that does not happen. Let's take two methylprimary radicals. So the two primary radicals mix and form ethane. So methane radicals mix and form ethane. So these are the three coupling mechanisms. So this process is the process of termination. So where you terminate the reaction. So these are the three main processes by which the reaction takes place. Now when you write down the net reaction, is what we write down as the final reaction in the series. So there are two main reactions that we are looking at in this mechanism. One is the initiation mechanism. Next is the propagation mechanism. And finally, we are looking at the termination mechanism. And if you only take the ones that we need to form the final reaction, which is hydrogen abstraction and halogen abstraction, that results in the net reaction that we see as CH4 plus Cl to form CH3Cl plus HCl. So remember that propagation is a chain reaction. So which means that the products of a later step or a later step serve as reactants of the earlier step of the mechanism. So for example, if you consider that some reactant created a product. That product then serves as the reactant for the next product. That product then serves as the reactant for the next product. So this process is the process of chain mechanism. So chlorination is a difficult process to prevent. So polychlorination is difficult to prevent. Methyl chloride is generally more reactive towards radical halogenation than methane. So what happens now? Methane is the rate limiting step of the reaction. So once the methyl chloride is formed, this is much more susceptible to undergo methylene chloride, more chlorination, so dichlorination. And that then is more prone to undergo trichlorination, and that then is more prone to undergo carbon tetrachloride, so tetrachlorination. So it continues as a process. So the first step becomes the rate limiting step of the reaction. So when we need excess methane, so relative to chlorine, for monochlorination to be the major product. So if you want just monochlorination, we need excess methane. So the common forms that we know are chloroform, which is CHCl3, and CCl4, which is carbon tetrachloride. Carbon tetrachloride is used as a solvent. So chloroform is used as an anesthetic agent. So there are different purposes for each of them. So the radical initiators is the ones that possess a really weak bond and that cleaves homolytically with heat or light. So most common ones that generally undergo easy radical initiators are acyl peroxides and alkyl peroxides after that, and after that we get dihalides. So dihalides need a lot more energy than in comparison to acyl peroxides. So acyl peroxides need much less energy to form radicals. And then alkyl peroxides are exactly in the middle between dihalides and acyl peroxides. So they need a little more energy than acyl peroxides. So acyl peroxide is the most reactive and it's the most effective at 80 degrees centigrade. So to create dihalides, we need a lot more energy. So to need a lot more energy, and we need to create a lot more heat. So the next ones are radical inhibitors. Radical inhibitors are the ones that react with radicals and prevent a chain process from initiating or propagating. So stabilized radicals and compounds that easily form stabilized radicals are generally good inhibitors. Best example of that is an oxygen diradical. So oxygen is a diradical that will react two other radicals. And hydroquinone is another substance that will also react with two different radicals. So remember that radicals reactions are generally very slow in the presence of oxygen. So when you have oxygen, this process does not occur. So most processes are anaerobic processes. So most processes occur under anaerobic processes. So now let's take an example of the radical inhibitor. So if you take hydroquinone and the radical that is there, the radical then undergoes hydrogen abstraction. So hydrogen takes its electron and the radical combines with hydrogen to form RH. So it has dissociated the RH structure and this becomes resonance stabilized structure. Now the resonance stabilized structure then again reacts with another radical and then forms RH again. So this then again, So again here hydrogen undergoes abstraction. So this hydrogen and then again is applied by the radical to form RH. It forms the intermediate structure that then undergoes more resonance stabilization to form benzoquinone. So this benzoquinone under reduction and then again forms hydroquinone. So these reactions help in understanding where we can stop the reaction. So if you want to stop the reaction at a particular process. Next, let's talk about the thermodynamics of halogenation. So if you wanted to determine whether the process is where product favored or reactant favored, we must determine the sign of delta G. So delta G here is the free energy of the system. So the formula for delta G is delta H minus T delta S. So it involves an enthalpy term and entropy term. So in general halogenation process, entropy is negligible because there is no change in the number of moles of the substance. So it generally requires more understanding of the enthalpy term. So here there are two molecules that then form two molecules back again. So there is no change in, so the change in entropy is nearly equal to zero. So we can relate delta G as nearly equal to delta H. So now let's look at the enthalpy term. So we can estimate the delta H based on the bond dissociation energy for the bonds broken. If you consider the methane and halogen, so it has to create CH3X and HX. So this is the table that shows you the bond relevant energies for each of these reactions. It's more common to form with chlorine and bromine than with fluorine. Fluorine is too violent, it releases too much energy, and it's generally impractical. But the same with iodine is too slow. So that's the reason why, because of less energy, it requires too slow. So it undergoes too slow of a reaction, so it generally does not form a favorable product. So delta H here is minus 431, which is too violent. Delta H here is plus 55, which is endothermic, also not favorable. So now we know that delta G depends on delta H. So we want it to be a spontaneous process. For a spontaneous process to be occurring, we need delta G to be less than 0. So which means that delta H should be less than 0. So the three reactions that are delta H less than 0 is 1, 2, and 3. But notice that this is too much energy at 1 per mole. So that's why this is too impractical. So reasonable amounts of energy are the chlorination and bromination. So these are the chances where the reaction might be, chances are high to create the reaction. So only halogenation with chlorine and bromine are useful. Next, both chlorination and bromination are exothermic, so which means that they favor the product formation. So they favor product formation. So if you consider the net reaction, which is the first process is hydrogen abstraction, which is negative 21. And the second process of chlorination, it is negative 96, so which creates negative 117. But in bromination, it creates plus 42 first, negative 92 first, so it creates negative 50 energy. So delta H for the first step of bromination is generally endothermic, and delta H for the second step is generally exothermic. But the net reaction is still exothermic, so that's the reaction why it's more favorable. But chlorination is the most easiest of the processes because it generally has both processes as exothermic process, so which means that the net energy released is much higher. So what happens here? So bromination is much slower than chlorination. The reason mainly is because the amount of activation energy. So this means that bromination is generally much more selective, so which means that it requires a specific set of compounds that it wants to first react with, or it requires a catalyst. But here for chlorination, it has much less activation energy in comparison to bromination, so which means that it is easier to occur. Next,